Sin x plus square root of cos x.
Okay. Dx as follows. And the way I'm gonna solve it is, of course, this won't be an indefinite integral. I'll do 0 to pi over 2. And the method will work in the way that inside a definite integral like this, what I can do is I can replace x, and instead of x, I can write a minus x when this upper bound is a, like this. When this upper bound is a, that means I will replace all x's inside the arguments by pi over 2 minus x. And this will help me in a way, in a nice way. This is the method I'll be using here. So 0 to pi over 2, and then I can replace the arguments. Right here, sine of pi over 2 minus x will be cosine x. That's how it changes nicely like this. And then I will have pi over 2 minus x inside this sine x. That will indeed give me cosine x again. And then plus cosine x, well, pi over 2 minus x inside this will cause it to be sine x. So this replaces as follows. But what's nice is now I see that these two things should be equal. I should be able to rewrite the integral with such a bound, with this bound, let's say in general I call it a. In such way that all the x's inside the integral argument will be replaced by a minus x. That means this upper bound minus x instead of just x itself. Well, I did that, and I know that if I, let's say, call this integral is equal to a, then this integral will also be equal to a. Alright? That means that I can basically take these integrals and say that they are equal to each other. But what is also nice is I can add up these two integrals. I know that if these are both a, then 2a will be the addition of these two integrals. That means 0 to pi over 2 of, well, sine x plus cosine x and common denominator. So that's square root of sine x, or in other words, square root of sine x, to be more concrete, plus square root of cosine x. And adding them, the common denominator cosine x and sine x right here. And what is really nice about this entire thing is it ends up showing, and this is a very concrete example, that's why it ends up like this, that denominator and numerator are the same. That means that all of this cancels out to just 1. Why is this useful? Well, I know that 2a means solution to the initial integral 2 times will be equal to this integral 0 to pi over 2 of 1 dx. Well, this will be equal to x evaluated pi over 2, which means 2a is pi over 2 namely, and then I solve for a because I said that the initial integral is equal to a. So a will be equal to pi over 4, and that tells me that the solution to this initial integral I had, thanks to the properties and thanks to the fact that it was this such an integral with bounds, namely 0 to pi over 2, thanks to that I can say that this integral is equal to exactly pi over 4.
Thank you.